Welcome back everyone. In this lecture actually we will study the finite dimensional representation theory of sl2c. So, I will begin with classifying finite dimensional irreducible representations of sl2c. So, then later in the next lecture it may not be possible to prove in this lecture, maybe in the next lecture I will prove the complete reducibility for finite dimensional representations of sl2c. So, let us start. So, we are only interested in this finite dimensional representations. So, let us take okay, let's first fix some notations. Let's start with what is sl2c. So, this lecture will be like a self contained. Okay, we don't need any knowledge from earlier lectures. So, sl2c is nothing but it is 2 by 2 trace 0 matrices over complex numbers. So, you start with all matrices 2 by 2 such that the trace of that matrix is 0. Okay. So, then we know that the dimension of this sl2c over C is actually 3 and it is spanned by the following elements. So, sl2c is spanned by, call it x, h and y, where x is this upper triangular matrix, h is this diagonal matrix 1 minus 1 and y is this lower triangular matrix. So, this is actually a form of basis over C. So, this form of basis sl2c over C. So, now we have already did some computation. So, if we actually write down the commutators actually of these elements, so then we get following table. So, if we just take, let us first write down what happens if I apply h on x. So, hx must be 2x and then hy must be minus 2y and then hh is 0. Okay. So, similarly we can actually write down table for other things. So, xy will be just h and xx is 0 and xh will be actually minus 2x. So, similar to that you have yx which is minus h, yh is 2y and then y is 0. Okay. So, we will fix this order. Okay. We take this ordered basis x, h and y. Then with respect to that you can see that so what will be the matrix of this add h. Okay. If you call this is B, so then the matrix of add h with respect to this basis. So, hx is 2x and then hh is 0 and hy is minus 2y. So, this is actually diagonal matrix given by this, okay, 0 0 0 0. So, this is diagonal. So, that means add h acts diagonalizably on sl2c, okay, that is what we get. So, similarly if you just compute the matrix of add x with respect to the same basis, you get this upper triangular matrix. And similarly for add y, we get this lower triangular matrix. Okay. So, this is just immediate from this table. So, from this table you can just write down this. So, this implies, so there are following observations. So, this add h is actually semi simple or diagonalizable or semi simple. Add x and add y So, both are nilpotent. So, this is the observation that we are making. Okay. We are looking at this adjoint action, okay, and then we are seeing that add h is diagonalizable and add x add y both are nilpotent. So, this will be actually useful later. So, I will actually make the connection between these things and how this element h, x and y act on any given finite dimensional space. So, for that we need complete reducibility. But anyway, let us see how these elements actually act on given irreducible representation. So, using this information we can actually classify all finite dimensional irreducible representation of sl2c. So, that is our goal. So, our goal in this lecture, okay, classify all finite dimensional irreducible representations of sl2c. Okay. So, let us start with some arbitrary representation and then see what we can actually say about that representation. So, let us fix some notation again. We start with V, finite dimensional irreducible representation of sl2c. Okay. So, that means each element in particularly the basis elements x, h, y they all act on V, okay, and the commutator relation should be actually satisfied. So, now so what we do, like we take the action of h on V and then try to understand what happens. Okay. So, first focus on the action of h on capital V. Okay. So, since we are working over complex numbers, our ground field is algebraically closed, this h must have some eigenvalue. Okay. So, let us say mu is an eigenvalue, okay, mu is an eigenvalue of h, okay, because if you take the characteristic polynomial of h, so that should have some root in over C. So, that is what I am calling it eigenvalue. So, in particularly, so there will be a corresponding eigenvector corresponding to mu. Okay. There exists some V non-zero inside capital V such that this action of h on V is given by mu V. Okay. This is the meaning of mu being eigenvalue. Okay. So, what we do, we also fix some notation. We say V gamma to be the gammath eigenspace of h. Okay. So, this is the gammath eigenspace of h. So, what is the meaning of that? So, this is those vectors w in capital V such that h acts on w by this gamma w. Okay. So, if you consider those vectors, so we are not saying that this V gamma must be non-zero. Okay. So, this is well defined space, it could be 0. When this is non-zero, the gamma becomes eigen value for h. Okay. Okay, note that V gamma non-zero implies gamma is an eigenvalue of h. Okay. But you know that there are only finitely many eigenvalues. So, only for finitely many gamma this V gamma can be non-zero. So, now this mu is actually an eigenvalue. So, we have this V which is corresponding eigenvector. Now, if we take this V to be eigenvector corresponding to the eigenvalue mu. So, we want to see how this x and y acts on V. So, let us first see how x acts. Okay. So, here is a small computation. So, we want to understand how x acts on V. So, for that we will just use the commutator relation and then see how it acts. So, indeed if you compute h acting on this x V, then using the commutator relation we get x acting on this h V. So, then there will be a error term. So, that is given by the commutator. So, that is h x dot v. So, recall the bracket h x is nothing but 2 x. Okay. So, in particularly so this is also the bracket h x can be written as h x minus x h. So, whenever you just commute these two actions, then you will get 2 x x like cost or the error term. So, in particularly by looking at this formula what you are getting. So, if you apply h on x v, then you get, because h v is already mu v. So, that implies that this first term becomes mu times x v plus this second term becomes, because bracket h x is nothing but 2 x. So, this becomes 2 x v. So, in particularly what we get, h acting on x v is nothing but mu plus 2 x v. So, what we indeed proved, so if we take v mu, which is the muth eigenspace of this action of h, then if I apply x on this v mu, then this takes this v mu to v mu plus 2. So, this is what we have proved. Okay. And this is true for any muth eigenspace. So, of course, if v mu is 0, then it is obviously true. When v mu is non-zero, the earlier calculation says that x actually maps v mu to v mu plus 2. So, similarly, one can do calculation for y. So, then what we get, if you do the calculation, again we compute the h action on y v, then we can see that this is just exactly y of h v plus the bracket x y v, which is exactly equal to mu minus 2 y v. So, that means, so this y takes the eigenspace v mu to v mu minus 2, the eigenspace corresponding to mu minus 2. So, this is again another important observation. So, what we have observed, so if we take muth eigenspace of h, then x maps that muth eigenspace to mu plus 2 eigenspace, and similarly y maps muth eigenspace to mu minus 2 eigenspace. Now, v is given to be finite dimensional. Okay, since dimension of v is finite, so we should have some k in z plus such that this mu plus 2 k plus 1 is not an eigenvalue, okay, is not an eigenvalue of h. So, we just saw that if you apply, like if you start with the muth eigenvalue eigenvector, if you apply x, then you get mu plus 2 eigenvector, and similarly if you keep applying x, so you will be getting mu plus 4, mu plus 6 and so on, those kind of eigenvectors. But at some point this x has to actually kill that the some power of x has to kill v, because we are actually working with finite dimensional space. So, recall this fact from elementary linear algebra. If you have vectors corresponding to distinct eigenvalues, so then those vectors must be linearly independent. Okay. So, that is something one actually knows from linear algebra. I will leave it as exercise to check. Suppose you have an operator acting on v. Okay. So, let us assume dimension of v is finite. Then if lambda 1 etcetera lambda r are distinct eigenvalues of t, and v 1 etcetera v r are corresponding eigen vectors, then one can prove that this v 1 etcetera v r must be linearly independent. Okay. So, now this obviously if mu is eigenvalue for H, then mu plus 2, mu plus 4 and so on, they are all like distinct eigenvalues if they are eigenvalues. Okay. So, that is why you get some k in G plus such that mu plus 2 k plus 1 is not an eigenvalue of H, but you can choose k minimal such that mu plus 2 k is actually eigenvalue. Okay. So, choose k minimal with the property that mu plus 2 k plus 1 is not an eigenvalue. Of H. So, what does it mean? It means actually mu plus 2 k is an eigenvalue. So, you can also choose such a way that this x power k v is actually non-zero. So, that like x power k plus 1 v. So, this corresponding to like basically the eigenvector corresponding to x power k v. Okay. So, what I want to say, you choose k minimal maybe with the following property, okay, then we get whatever we wanted as implication. So, choose k minimal with the property that x power k plus 1 v is 0. So, but x power k v is non-zero, okay. Such a k we can choose because dimension v is finite dimensional. So, now with that k, what we can do, we can actually take lambda to be mu plus 2 k. Okay. So, then what happens? Then if you take this v naught to be the eigenvector corresponding to that. So, that means it is exactly this x power k v. So, then it is easy to see that this h acts on v naught as lambda v naught and x acts on v naught as 0. Okay. So, we replaced this v by v naught, so that we got this additional property. This h is acting on v naught as lambda and x actually kills this v naught. So, this kind of elements will be called maximal vectors, okay, of weight lambda. So, this is again like maybe we will define it in general finite dimensional representation of sl2c, okay, but I will make a note. So, this kind of vectors will be called maximal vectors of weight lambda, okay. Again weight with respect to only h. So, now you can see that we have actually created one non-zero vector where h acts as lambda and x actually kills. So, we need to understand what happens if I apply y. Okay. Of course, if I apply y, all I have is I can take y v naught. So, for sure I know that this will lie inside v lambda minus 2. Similarly, y square v naught, again this will lie inside lambda minus 4 and so on. So, that is our earlier calculation says. Again what we can do, we can choose r such that, so now choose r again minimal such that this y power r plus 1 v naught is 0, but y power r v naught is non-zero. Okay. So, then you can see that if I apply, like if I start this with this vector v naught, okay, if I am interested in actually submodule generated by this v naught. So, what is submodule generated by v naught? It is actually a intersection of all modules that contains v naught. So, if you apply various actually elements from this sl2c on v naught, so it has to be inside that whatever submodule. Okay. So, let me call w is a module that contains actually v naught. Then what will happen, because this is actually sl2 submodule. Okay. So, if I take any element of this SL2, okay, then if I apply it to this V naught, it has to be inside W. So, in particularly for example, if I take xi1 and then xi2 and so on, xik, and then if I apply it on this V naught, all of them should be inside W, okay, for any xi1 etc. xik inside your SL2C. So, indeed one can prove that submodule generated by V naught will be exactly collection of or the span of all these vectors. Okay. So, we are actually interested in looking at this submodule generated by V naught, but surprisingly because SL2 is actually a very small Lie algebra and the commutator relations are actually so tight. So, if you are looking at this submodule generated by this V naught, it is not that hard to actually find out. Okay. So, for example, you can actually the way we actually chosen this V naught, H is going to act actually as scalar and x is going to kill. So, if you apply any powers of x, that is going to kill this V naught, and if you apply any powers of h, so that is going to actually leave this V naught as like it is going to leave this span of V naught. Okay. So, then it actually somewhat suggests we need to only worry about only the powers of y, but powers of y we do not have any control, but we have made some choice. So, we have made a choice r such that y power r V naught is non-zero, but y power r plus 1 V naught is actually 0. So, then look at this cyclic space generated by this V naught, okay, using this operator y, and then see what is happening. So, you take this space which is span of V naught, y V naught and so on y power r V naught. Okay. So, this is sits inside V. So, call this is actually V dash. So, we claim that this is actually going to be submodule generated by V naught. Okay. So, our claim V dash is indeed SL2C submodule. Okay. If it is SL2 submodule, then because V is being irreducible, so that forces that V has to be equal to this V dash. Okay. So, that is why we are establishing a submodule generated by this V naught, and then we are actually trying to see what we get. So, this is actually very explicit basis that we are actually establishing using this construction. So, because this V naught, y V naught etc., y r power V naught, they all corresponds to distinct eigenvalues of H. Okay. So, the V naught has eigenvalue lambda, y V naught corresponds to eigenvalue lambda minus 2 and so on, y power r V naught corresponds to eigenvalue lambda minus 2r. So, these are all H eigenvalues. Okay. So, obviously, they are linearly independent, or otherwise because we have chosen R such a way that this y power r plus 1 is 0 and y power r is non-zero. So, that also like gives us, because this is a cyclic space corresponding to this operator y. So, you can prove that this will be linearly independent. I guess that is also true. Okay. So, let us move on. So, anyway, because they corresponds to distinct eigen values, so they have to be linearly independent. So, if you just look at it, so y obviously maps V dash to V dash, because y will just increase the power. So, if you apply it on this spanning set, it going to increase the power. So, it will be invariant. So, there is no issue, and H is also going to leave it invariant, because each one of the spanning elements, so they are all eigen vectors for H. So, that is also fine. So, the only non-trivial thing we need to check what happens if I apply x. Okay. If we prove that x also leaves V dash invariant, then V dash becomes SL2 submodule. So, let us see what happens. So, if I apply on V naught, it is going to give me 0. So, there is no issue. So, if I apply it on y V naught, let us compute what is happening. So, then I am allowed to switch. So, I will get y x V naught plus bracket x y V naught. So, then you get, since x is killing V naught. So, this is 0 plus bracket x y is actually h. So, you get h V naught. So, h V naught is nothing but lambda V naught. So, x y V naught is actually given by lambda V naught. So, this is the second term, this is the first term. So, if you compute again x y square V naught, let us see what is happening. So, this can be written as just x y y V naught. So, then this y x sorry x y can be switched. So, this can be switched as y x applied on y V naught plus the bracket x y applied on y V naught. So, then you can see that. So, this is actually can be computed using this formula. So, then because this is actually given here. So, then this is y x y V naught, which is lambda V naught plus this bracket x y is h. So, this gives h y V naught. So, then h y V naught is nothing but lambda minus 2 y V naught. So, you get lambda y V naught plus lambda minus 2 y V naught. Okay. Because h is going to map v lambda to v lambda minus v. So, this is eigenvalue y maps v naught to lambda to lambda minus 2 eigenspace. So, that is why you get h of y V naught is as lambda minus 2 y V naught. So, this says this is x y square V naught is nothing but 2 lambda minus 2 okay, times y V naught. Similarly, you can actually compute y cube and then see what happens. Okay. So, let us compute and then see what happens. So, if you compute x y cube V naught, then this is, you can write it as again x y square, we have to go step by step, x y y square V naught. So, then this is y x y square V naught plus you can see this is h y square V naught. But it is clear that this is already computed using induction. So, this is y 2 lambda minus 2 y V naught plus this is nothing but lambda minus 2 y square V naught. Okay. So, this gives me 2 lambda minus 2 plus lambda minus 2 y square V naught. So, if you just compute and see, this is 3 lambda minus 4 y square V naught. Okay. So, this actually clearly says, so by induction you can prove that x y power k V naught is actually in the span of lower terms. Okay. That is all we need to do, but it is actually saying it is actually one term down. So, maybe I will leave it to you to check x power y k V naught. So, using now induction, you can prove this is in the span of V naught, y V naught, etc., y power k minus 1 V naught. Okay. This is true for all 1 less than or equal to k less than or equal to r. So, this proves that if we take this V dash, which is the span of this V naught etc., y power V naught, that is actually SL2 submodule. So, that forces this V dash to be equal to V. Okay. So, let me just write it down. So, this indeed proves this V has to be equal to span of V naught y v naught etc. y power r v naught. Okay. How the action of h, x and y are given. So, you can easily see that if you call this v I to be y power or I v naught. So, then it is clear that, so y actually increases the power. So, it means y v I is just v I plus 1. So, that is easy to see, and then h v I is actually going to give me lambda minus 2 I v I, because every time h is going to act by like it will reduces actually the eigen value. Okay. So, sorry, this is actually, so if we just go back to the computation, so what we actually seen, yeah, h y v will be just mu minus 2 y v, that is correct. Yeah, so that means, so this h v I will be just equal to lambda minus 2 I v I, and what will happen to x, again from this earlier computation you can actually guess the formula. So, x v I will be exactly equal to I times lambda minus I plus 1 v I minus 1. Okay. So, here we set actually v minus 1 to be 0. Okay. So, because that is used in this formula. So, only thing that is actually required to be checked. So, first formula is fine, second formula is also fine, the third formula is needs some checking. So, let me do it. So, this is again by induction. So, you assume that x v I is equal to I times lambda minus I plus 1 v I minus 1. Okay. Then if you just calculate what is x v I plus 1. So, that is nothing but x y v I. So, then you can actually swipe these two. So, you get y x v I plus the bracket x y v I. So, then y x v I will be become, okay, because you can use this formula. So, this is I times lambda minus I plus 1 y v I minus 1 plus h v I. So, this is going to give me, so y v I minus 1 is nothing but v I. So, this is going to give me I times lambda minus I plus 1 plus h v I will be lambda minus 2 I times v I. Okay. Then if you just group it, you can see that, so this is going to give I plus 1 times lambda minus I v I. So, that proves that this x v I plus 1 is nothing but I plus 1 lambda minus I v I. Okay. So, this actually completes the proof of this identities. So, this actually proves this v has to be equal to the span of this v naught, y v naught etc., y or v naught. Okay. So, by looking at these formulas, you can actually see that this y power r plus 1 v must be 0. Okay. That is how we have chosen this r. So, y power r plus 1 v, okay, naught should be 0. So, now if you just look at it y power r v naught, then what happens? Okay, y power r v naught. So, that must be non-zero. But then if you just compute what is x v r plus 1. So, that is nothing but x applied on y power r plus 1 v naught. Okay. So, since y power r plus 1 v naught is 0, one side you get 0, but on the other side you get this formula, because this is going to reduce it to 1 power down. So, this is going to be r plus 1 times lambda minus r v r. Okay. So, look at this formula. So, that means r plus 1 times lambda minus r y r power v naught must be 0. But since this vector is non-zero, that forces r plus 1 times lambda minus r is 0, and that forces lambda must be r. Okay. So, this is actually a very striking fact. Okay. So, this fact actually tells lot about what could be this eigenvalue lambda. Okay. So, basically it says it must be non-negative integer. So, this r could be 0. So, because of that, so we are actually we proved this is indeed non-negative integer. So, this actually immediately proves the following things. So, all eigenvalues of V, okay. So, with respect to, okay, maybe let me write it as H eigenvalues. All H eigenvalues of V are integers. Okay. So, the very first actually, so this is only second, the very first assertion H acts diagonalizably on V. Okay. Second is all H and eigenvalues are integers. The third thing is the eigenvalues also can be listed. So, the eigenvalues are r minus 2 and so on up to like minus r plus 2 and minus r, because this is corresponding to V naught, this is corresponding to y V naught and so on. This is y r minus 1 V naught, this is y r V naught. Okay, this is the correspondence. So, this also tells that what are the eigenspaces dimensions. So, this actually proves that all eigenspaces are all one dimensional. Okay, all these facts are actually follows immediately from observing that lambda must be an integer, and this is indeed a basis. This V naught, y V naught, etc., y power r V naught is a basis of this capital V. So, let me summarize. So, this is very, very important. So, if we start with, so can we recover this R? That is also one important thing. So, if you actually think about it, this is actually what is the dimension of this space. So, the dimension of space must be just R plus 1. So, this tells this R also can be recovered. This R is nothing but dimension of V minus 1. Okay. So, this R in some sense captures everything about this finite dimensional irreducible representation. So, what we did? We started with finite dimensional irreducible module of this sl2c, and then we established this basis for this representation, which is generated by this V naught. So, V naught, y V naught, etc., y power r V naught. Okay. So, then we actually proved that how each element of this basis elements of this sl2c acts on this basis of this capital V. So, indeed if we denote this by V1, V2, etc., V r plus 1. Okay. So, maybe we denoted by V0, V0, V1 and Vr, then we can see that V0, V1, etc., Vr minus 1, Vr is here. So, Y basically maps 1 up, okay, and then H maps into itself, and H x is actually mapping the other way. So, this is how the entire action is actually given. Okay. So, that you can read it from this table. So, this all the action of y, h and x are very explicit on this basis. And we also observe that the highest weight vector or the eigenvalue. Okay. So, that must be an integer, okay, non-negative integer, and all the rest of the eigenvalues or the weights of this h. So, they are all actually decreases by 2. Okay. So, you start with r, you just every time you decrease by 2, then you reach minus r. Okay. And all the eigenspaces, they are all one dimensional. So, these are all very important consequences of our analysis. Okay, I will stop here. So, we will actually use this information to completely classify finite dimensional irreducible representation. Okay. So, I will continue that in the next lecture. Thanks.